record. So okay, so today's uh, tutorial is is about training, model training and hyperparameter tuning in particular. So yeah, so I'll just like go over a few concepts basically. Here, you have already probably come across this and thought about concepts just like how these are played out in or how you do this basically. So yeah, in short, like of course, the main thing here is about hyperparameter tuning. So what are hyperparameters? So when you're doing any machine learning, you're training any machine learning model, they are essentially during the training, the model is learning, is affecting some of its parameters um, during the learning. So during the training, it's like it's changing its parameters so such that it's like to make its the prediction um, as like that it's to with lowering the loss function, as you understand that part. But there are parameters that are not fixed during the learning. These are parameters you have to fix manually beforehand when you're defining the model itself. So think about like, let's say, let me stop sharing and share my whole, maybe my whole screen. 1 second. So yeah, instead, so that I can just open the links and show you this. So there is nothing particularly like already understand it. Probably whenever you're using any model, there are parameters you need to fix beforehand. For example, in logistic regression, there are like parameters that you can see this. If you, for example, in this scikit-learn library, the logistic regression model, the classification model, um, is this is how it is defined, and you can see there are parameters here that are fixed, or like they have default values, but you can change them, and one of them is the C value, which is the it's the inverse of regularization strength. So it can have values you can see here. It can must be a positive float number, okay? But its value basically can change the performance of the model, but you have to choose it when you define, when you like you are defining the, when you are like defining the model, or like before you're training it, before training it, right? So there is a, like if you use it directly without defining C, that means you're using it with the value of 1, but it might be your model will perform better if we at a different value, right? So C is a hyperparameter, and fixing it, or basically choosing the best value, is what is called hyperparameter tuning. Okay, so there are other, like in cases of the decision tree, there is the maximum depth, for example, the minimal sample split, minimal sample leaf, and like the definitions of those, like you can look through, like, you know, how the decision tree works. And basically these parameters are like the maximum depth, the maximum depth of the tree, the minimal sample split, the minimal sample required to split at an internal node, and minimal sample leap is the minimal sample required to be at a leap node. So basically you can, so they see like that each value has, each hyperparameter has a default value, but you can change it. Of course, you have to choose like the maximum depth for your decision tree model. And basically these choices, because when if you make them initially, you don't have, maybe you have some intuition of what could work better, but you don't No, and you cannot learn through the training. So you have to basically pick them or search for the right um, value for, or the best values for hyperparameter. And basically this is what is called hyperparameter tuning. So it's part of the learning, basically, what you do. Uh, you can start with like a particular value and say like, okay, I'm done with this. But if you are really looking for the best model to work with, it's recommended that you look for like in the space of hyperparameter values and see which one perform better. And you can do this systematically using cross validation. So what is like before, like we'll talk a bit about cross validation in a bit. So what you need for hyperparameter tuning, you need a model, and each model has its own hyperparameters. For each parameter, you need a space. So like what values are going to search for, um, um, for a value, let's say, for the C value in the logistical regression, say you're going to look for values between 0 and 100 or whatever, or like whatever values you are looking through, you're going to look through. You need a method for searching. You need a cross-validation scheme. Again, we'll talk about this in a bit. And then the score function, how a metric basically to determine which model is performing better. Okay. And so this just to mention hyperparameter tuning, like there is a grid search. Like this is like there are two major approaches, but like there are also improved approaches from these two. One is grid search, is like you look, think that you have like let's say you have two hyperparameters, and for each hyperparameter you have like let's say 3 values. So then all possible combinations of these are going to be 3 by 3, which is 9, right? You have a grid of 9 values, of 9 possible combinations, and you look through each one of them. So you train your model for each combination and then compare. So this is what is called a grid search. Randomized search, in this case, you sample from your spaces, you sample a number of candidates from your parameter space and look at this. So what is the difference between the two? Of course, like you might think like, okay, grid search is great because I'm looking for each possible combination. I'm going to know for sure what is the best combination of values. But of course, you can see directly why this is, what is the downside of this, which is that it is computationally expensive, right? If you are training a model for each combination, this is a lot computationally. So especially if you have multiple hyperparameters and your spaces are big, so instead of 3 values for each of the two, you think you have 3 and each one has like, you don't want to look in a space that each has, I don't know, 10 or something, and then you're going to have 10 to the power of 3, which is 1,000, and you don't want to train 1,000 models, right? Randomized search, instead, you're going to sample just a few of these possible combinations you have and just look through those. And because it's randomized search, you like have a chance of coming across like good values. There are like improvement of over both of these, so that you can have a randomized search that is have better chances of finding the best hyperparameters for you. Okay, so this is just blah blah blah. So in a bit, can see an example of doing this, and it's not very okay. So I was mentioning cross-validation over multiple times before. So what is cross-validation? What is validation? So when you are training your model, you already probably know about this, that when you train a machine learning model, it's important that you separate your data into a training set and a test set, and you train your model only on the training set, and then just at the end test on your test set to find its performance, right? Because like if you train your model over the whole data you have, you don't split it. Basically, what you measure in the end is not going to be of any meaningful value, right? Because it's like this is a data that the model has already seen during the training, and if you just choose a model depending on how well it does on its training data, this is not, it's going to be you're choosing the model that is most overfitting, right? Because the model that will perform the best is the one that basically memorizes the values for the training set itself. So it's overfitting because it will work very well for the training data, but it's not when it's going to come across and seen data before, it's not going to be performing as well. So you need to split your data into training set and test set, right? But this is when you are training a model just without hyperparameters, or you're not tuning the hyperparameters. When it comes to tuning the hyperparameters, how are you going to choose between different values of hyperparameter? Like you split your data into training set and validation and the test set for a particular value for the hyperparameter. Let's say we're using logistic regression, and you have this hyperparameter C, and we want to take values of C equal to 1 and equal to 10. Let's say, we're just going to test these two. And then we train the model for the first value of C, and then test it on the test data, and you find some value. And then we again train the model for with C equal to 10, and again test it on the same test set from before, and we get some performance value. And then we compare the two and say like, okay, C equal to 10 perform better. That means this is a better model. But here again, we are again overfitting because we are choosing the model, because like these two comparison between different values of hyperparameters is again a kind of training, and we are not testing our best choice of hyperparameter on completely unseen data from before. So instead, we need what is recommended is to split your data into 3 sets: training, validation, and testing. Basically, you're going to do the training with different hyperparameters and compare the performance of different values for hyperparameter on the validation validation data. And once you choose the hyperparameter, the value you think is performing better, you test it on the testing set that was completely unseen before, and to see how it actually performs on completely unseen data from before. Right? So this is good. So this like seems like, okay, we're again just an extra split is not a big deal. We can do that. Of course, you can see the downside of this because we are now dividing our data into 3 data sets. We are reducing the training data to begin with to an even smaller size, which means like our model are not going to be, we know that like the more that we have, the better our model is going to be. And we're reducing the data means that like we're getting less data to use, which is not a good thing to do in general. Another thing, and this is like can cause a problem as well, is that depending sometimes like the performance of like our hyperparameter will depend on this split. If the split is not will depend on the split. Like it's completely going to be depending on how you split the data and which data is going to fall in the training, which one is going to fall in the validation. The performance will depend on that, and so it's still going to be overfitting in a sense. And to avoid that, we come across what is called cross validation. So what you see here is one sort of cross validation. So what is cross validation? Cross validation is basically, instead of splitting the data in 3 data sets like this in a particular way and doing the thing that I was describing before, training and choosing the hyperparameter depending on the validation data set, and then in the end testing on the testing data set. Instead, we combine these two like before. This all is a training data set, and do random splitting in different ways in the training and basically validate on that. So one, I will just explain one example, is called a k-fold cross-validation. In this case, this is 5. So what we do, we have all of our data. We have a training data. We split it in 2 parts, like the training data and test data, let's say 70-30%. And then in the algorithm, we're going to do is going to divide the training data into 5. In this case, you choose the value of k. So we choose the value of k to be 5 here. That means the training data is going to be split into 5 sets. And we're going to do 5 iterations. In each iteration, you're going to set out one set, let's say fold 1 in the first iteration, and train the model over this of the remaining 4 and validate over this, the first one that will remain. And then in each iteration, we're going to leave out one fold or one part of the data, different part of the data, and train over the rest. And then by the end, after we do the 5, we average over the values of the performance for all of these 5. And then we do on the test again. Here you can see like we did more training basically with random splits. So we randomize the splits and we increase our data set in the training data set in a way. So we solve both these problems. Of course, there is only one drawback, is that we are doing more, again, computationally. This is more expensive than just training on that whole training data set one time, right? So there are always like, you have to balance between like getting less bias or less overfitting and the computations you want to do. You have to choose the right kind of model and right size of data on all of that. You have to take into account multiple things, but you have to know the benefits and the drawbacks of each choice you're making, right? So this is in general. There are other kinds of cross-validation, and so there are different types. There is a k-fold. This is the one explained. This is a basic one, but there is a holdout, the stratified k-fold, leave p out cross-validation, leave 1 out. So these are different ones. So, and you can see like this is one explained from before. In the holdout one, okay, this is like this is actually the most basic. So it's not really cross-validation, but like let's say stratified k-fold. Here, like which time we have. So okay, so just to not instead of doing completely, the split in the k-fold is completely uniform, basically across also all the data has the same probability to be in whatever fold of the data. And instead of that, we can make sure that we have a better representation of the data we have. For example, here in the case, you see like this classification case, and in a classification case, in the training data, you want to have like a reasonable representation of the data. So let's say if the data has the target you want is like has this kind of distribution of, like, let's say in this case it's a male against female, instead of having, like, if you do just uniformly, just a normal k-fold, you will find like maybe some of your fold will have like so many, like so much like completely male or completely female, and it doesn't reflect the representation you want. And instead of that, if you want to just guarantee that the folds you have, the ones that you leave out, are representative, you want to change the distribution, basically, so you don't get unrepresentative split of the data. And so forth. You can look through and see like different kinds. So just to work it out, basically. So this is a generic thing. So of course, when using scikit-learn library, you can do the cross-validation and grid search. There are like classes for doing this, basically. So in this example, we're working with the iris data. So it's a classification. The iris data, of course, it's like very basic. These are data for 3 species of flowers, and the features are the length, width, and the length and width of the petals of the flowers, and then the target is classification of the different flowers. So we want a classification model here. For example, we're using the support vector classifier with this particular kernel. And in each, so yeah, here I loaded the data set and separated the features from the target. And in each model in scikit-learn, you can see the parameters, your hyperparameters, with this function get params. You can see it. So you can see these are all hyperparameters, right? And you can change like the default the values for them at the moment. Let's say we take 2 parameters. We take the C parameter from before and also the gamma parameter here. And we set the space for we're going to do a grid search. So we set the values we want to look through. So for C, we want to look through values 1, 10, and 100. And for gamma, we're going to see values 0.01 and 0.1. Okay. Again, you can look what is the meaning. Just look the model, and like in the documentation, you can see the possible values. It's not this one. Let's see. So in the right, so this is a model I'm looking at, and you can see, yeah, so this is the regularization parameter, this is the C, and it must be strictly positive. This is a possible values for it, right? If you just understanding the hyperparameters is important before you do any tuning, of course. Like you need to understand what it means. So okay, what did I also said? So the gamma is a kernel coefficient actually. It has like okay, so it's if it has to be non-negative float. So just I'm just going to look at like defining it. So it's the kernel functions of the support machine, support vector machine, and you can see what's the gamma here. It appears here in some of the kernels because we are using this RBF. This is what gamma for us here. So here it has to be greater than 0. So this is what we are looking for, or this is what we are trying to tune, basically this gamma. Yeah, so just like not deep understanding, but just understand what is a parameter and what is a possible value and whether changing it. Like you want to choose like ranges that are like will do some difference. Of course, you can do this by trial and error, but you can also, it's better to understand what you're doing, basically. So here, we're going to be doing cross-validation. So it's a k-fold. So for a k-fold, you need to determine the number of splits. Here we're using 4. And we are going to be doing like setting the random state. We're going to do like a 30 or a number of trials. So setting this random state to I. And what we're doing here, so there are two of them. We're comparing here what is called a nested cross-validation and a non-nested cross-validation. So the nested cross-validation is what we mean to look at, which is the one we are tuning the hyperparameters. And so we're going to be using the grid search. This is the cross-validator. So grid search CV. So the estimator is a model. So SVM, which we defined before. The parameter grid is the one that we define here, these values, right? And then we're going to pass it the k-fold cross-validation here, right? And so in each we are going to compute the score, right? Which here is the accuracy, and pass it, of course, the like the data we have. So yeah. And we compute basically the mean of the scores we have. Right. So you can see like it's really it's not taking much lines in code, basically. So there are like have the tools to use directly. What you need to understand is just like, as I said, which hyperparameters you're going to be tuning, and like these different the cross-validation way you're going to be using, and the score you're going to be like measuring for to differentiate or to choose which values you want, basically. Okay. So any questions so far? Anything that need to be looked at? Okay. Just as a note, in this code here, they are doing the nested cross validation. So what I explained for before is, as you can see, like if you can ignore this basically, and this part, this is a basic thing to do. So basically, you split your data with a k-fold, right? And the grid search is going to, what the grid search is going to do is going to be like um, going through like the grid. So it's a grid search. So it's going to go over all the values and the combination of values, and is going to be doing the basic cross validation, which means that for each combination, it's going to be um, uh, training the model over um, uh, over like the four, like leaving only one and training over the rest, and then validating over the left out fold or the left out set, and then like comparing between the different hyperparameters, different values of hyperparameters, and giving you the best scores. Like this gives you the best score for each, like of like the best performing model with the best how to say. So if we run it, just that shouldn't take much. Let's say we run this in okay. Let me just set random state to 1. Am I doing something wrong here? Okay. And then let's say this is what I want actually. Parameters. You can see the best parameters you get from this is like c equal to 10 and gamma equals to 0.1, and best score. This is the accuracy for this the best model, right? Yes. Is there a question? Anyway, so I hope this was like I don't know. You didn't ask any questions, so I don't know if this was too basic or like it was probably it wasn't too quick. Well, this was really um hopefully it was useful. So do you have any questions, any final questions, anything? So, or let me just ask, it doesn't have to be about this tutorial. It can be just about what you're going through with the project. Probably this is task 5, so this is still, maybe you haven't reached this task just yet. So what about the rest of the project? How is it going for you? I'll give you a couple of minutes just to think, and then we can, if there are no questions, we can just end the tutorial. Okay, so I will let you go and this recording. And